Hello, ladies and gentlemen. This is a Unit 7, Day 1, and we're going to start talking about trigonometric ratios, okay? So before we can start talking about that, we need to mention something about similar triangles, because similar triangles allow for this thing to happen. And more importantly, similar right triangles, right? Right? Yeah, no pun intended. But anyway, trigonometry is only involving right triangles, okay? So you can forget your isosceles, forget your equilaterals. We're only talking about right triangles when we're referring to trig, okay? When we're finding missing sides and angles, all right? So before we get started with those, I want to discuss what it means to be a similar triangle, all right? And so there's three criteria that we look for in order to say triangles are similar, right? Now, what does it mean to be similar? Okay, we will discuss that once I get to the examples here, okay? But for two triangles to be similar, okay, all three pairs of corresponding sides of the two triangles are proportional, okay? That's one of them. Okay, another one is two pairs of sides of the triangles are proportional and the angle included between the proportional side is congruent. Okay, then the two triangles are similar. And then finally, if two angles of one triangle are congruent to two angles of another triangle, the two triangles are similar. Okay, and so this one really allows us to do what it is that we're going to be doing in this unit. So we'll come back to this one later in the lesson here. But for now, know that this criteria allows us to do what we do here in trigonometry. Okay, but before we talk about that one, let's talk about what it means to be similar triangles, right? Let's show a couple examples. Now, if you remember the term dilation, okay, dilation is something that preserves shape but changes the size, right? Remember rigid motions, they preserve size and shape, okay? Dilations, excuse me, dilations preserve shape, but as you can see, they don't preserve size, right? Remember, this one is getting bigger, and this one is getting smaller. But both shapes are the same, just different sizes, right? So that's how you could kind of look at these similar triangles, right? They have similar shapes, but their side lengths are different, right? So if you look at A, okay, these are a couple similar triangles, right? And we know this because all of these sides here are twice the amount of these guys, okay? So we would call these proportional, right? In the sense that, you know, this right here, this side right here is twice the amount of this side here. This side here is twice the amount of this side, and then this side down here is twice the amount of that side. And so that lets us know that these two triangles are congruent because all of these sides in DFE are twice the amount of the same corresponding sides in ABC. Okay? Now, we look at letter B, right? This one kind of, so this A, I would say this one would be side, whoops, side, side, side. Okay? Now, we will work more with dilations and similarity in our next unit, but for now, I'm just introducing what it means to be similar. Okay? And also the symbol for that, okay, looks like this. All right, you've seen this symbol before. It appears in your congruent sign, okay? Except, again, these two triangles aren't congruent, right? They don't have the same size and shape. They just have the same shape. So therefore, we can only say they're similar, right, in the sense that they have the same shape, but they don't have the same size, okay? So this is the symbol for similar, okay? I think there's an I in there, right? Similar. There we go. Okay. So anyway, no, there's not. Hello. Anyway, let me put the symbol up here, okay? Anyway, all right, so these guys, okay, are also similar triangles because they have a congruent angle in between, and then also these sides are proportional to one another, okay? Proportional in the sense that 10 over 15, right? Well, that's just going to be 2 over 3, and 14 over 21 is also 2 over 3, okay? So the ratio here would be a 2 to 3 ratio, or over here this would be a 2 to 1 ratio, right? In the sense that these are just a little bit bigger than the other ones, right? But not by much, okay? So if you figure, right, all these sides up here in order to get these ones down below, I would have to multiply this by 3 over 2. Multiply this by 3 over 2. And by doing so, we would get those same values down here. Okay? So therefore, because we're able to multiply it by the same value for both sides, for both AB and BC, therefore we can say that B or the triangles in B are similar by side angle side. Okay? Now, let's get down to some nitty-gritty here. Okay? So in exercise 1, it says consider the two right triangles shown below. All right? So how would we justify that triangle ABC is congruent to triangle DEF? Okay? Be clear on your explanation. Well, because all sides are proportional, we could go side, side, side. Okay? Because angle A is congruent to angle D, based off what I wrote up here, as you can see. Okay? Then we can also say that these two triangles are similar because, we can say, okay, we can either use angle, side angle, right? Or side angle side, sorry. Or, because we have two congruent angles, right, both having a 90 and having the same angle over here, we can just say side angle side or angle angle. I think that's what it's called, right? Angle angle criteria. Okay? So in retrospect, we can actually use all three here. Okay? So it depends on, well, what you're comfortable with and what information they give you and what you're looking for. So in this case, all three criteria would work in the sense that all three prove that these two triangles are similar. Okay? And again, as you can see, right, these sides here are just double the amount of the other one here. So this would be a 2-to-1 ratio. Okay? So it says determine the values of the following ratios. Express your answers in the simplest form. Okay? So before I get started with that one, I want to list what it means to be a ratio. Okay? So a ratio is this. Okay? A ratio is the quantitative relation between two amounts, okay, showing the number of times one value contains or is contained within the other. Okay? It's important to know what it means to be a ratio. All right? Basically, it just means how much of one value can fit inside the other or how much is contained within the other. Okay? So, anyway, going back to letter B, it says determine the values of the following ratios. Express your answer in the simplest form. Okay. All right, so BC over AB, so it's going to be 3 over 4. Okay, BC over AC, that's 3 over 5. And AB over AC is 4 over 5. Okay? Now we're going to take a look at the same ratios created by that similar triangle. Right? And hopefully you'll notice a pattern here. Okay? So EF is 6, DE is 8, but when we simplify that by 2, we get 3 over 4. EF, 6, DF is 10, but again that simplifies to 3 over 5. And DE is 8, and DF is 10, and again it simplifies to 4 over 5. Okay, so hopefully we notice here that when we have similar triangles, these ratios created by these sides, when we're setting them up on top of each other, actually end up being the same number, right? And so that will tie in to later concepts here. But what's important is that these ratios created when we line up these sides on top of each other, right? When we set up these ratios amongst these sides, okay, for the similar triangle, we end up getting the same exact number, which is pretty cool. Okay, so it says place the value of each side length in the table below, then calculate the ratios in the table to the nearest hundredth. Okay, so let me put all these in here. So BC is 3, AB is 4, AC is 5, this is 6, 8, and 10. And when you simplify these, okay, BC over AC, that's 0.6, EF over DF, because they're both 3.5, that's going to be 0.6. This one's going to be AB over AC, this is going to be 0.8, this one's also going to be 0.8, and then this one's going to be 0.75, and this one will be also 0.75. Okay? So it says the ratios you've calculated for the two triangles should be equal. Why is this? Explain carefully. Okay? Because triangle DEF is proportional to triangle ABC by a 2-to-1 ratio. Therefore, the fractions or ratios, we'll say, simplify the same decimal. Okay? So they end up simplifying, not to the same decimal, the same fraction, sorry. Okay? So because DEF is proportional to ABC by a 2-to-1 ratio, meaning that all the sides are just double the amount, therefore these ratios, when we simplify these fractions, should simplify to the same fractions or ratios we got from triangle ABC. Okay? So it says, using your work from A, determine the lengths of ST and TR to the nearest tenth. Show how you arrived at that answer. Okay? So what we're going to have to do is we're going to have to set up some proportions. Okay? So what they're saying is these two triangles are congruent, or RST is, or not congruent, similar to ABC and similar to DEF. Okay? Meaning that their sides are proportional. Okay? And all of their angles are, well, essentially the same, right? In order to preserve shape, all the angles must be the same. Okay? So, therefore, right, and we kind of wrote that right there, right? They got the same angle there, right? If that's the same here, that's the same there, yada yada, right? So anyway, here's what we're going to have to do. So I'm going to set this equal to x, and I'm going to set that equal to y, because we don't know what those are yet, okay? So I'm going to set up a proportion. So I'm going to go x over 18, okay, is equal to. So I'm going to go back up to the top, and I'm going to use this triangle right here, okay? So what side am I trying to find? I'm trying to find RT. So I go up to the corresponding side. And so that would be 5. So the corresponding side for RT in triangle ABC, okay, is AC. So that one's 5. The length of AC is 5. And the length of AB is 4. So we set up that proportion, cross multiply. We get 4x is equal to, I don't know, 18 times 5 is 90. Divide that out. X is equal to 22.5. Okay? And so that's what this guy is equal to. And then y, we're going to do the same thing. So y over 18, we're going to go up to that corresponding side. So BC is that corresponding side. So ST is the side we're looking for. So 3 over, again, 4. And we cross multiply, so we get 4y is equal to 54. And so y is equal to 54 divided by 4, right? 13.5. Okay? All right. And so that's how we can find those missing sides using these proportions and knowing that these triangles are similar in utilizing those corresponding sides. Okay? So because all right triangles that share an acute angle are similar, the ratios of sides and the ratios of the sides of a right triangle don't depend on the size of the right triangle, but only on one of the acute angles. So these ratios are known as trigonometric ratios and are defined by the relative positions with respect to the angle. Okay? So what they're saying is this: because all right triangles that share an acute angle are similar. Okay? That ties back into this guy right up here. Okay? Because if they think about it, if they got one angle, so if this is 35 and this is 35, okay, but we know they're both right triangles, well, then we could say those two triangles are similar because we know that they have two congruent angles. Okay, so the same concept kind of flies down here, right? When you have two right triangles that share the same acute angle, in this case A, okay, the ratios of the sides of the right triangle don't depend on the size of the right triangle, but only on one of the acute angles. So because these right triangles, okay, end up being all kind of similar, and you end up getting the same ratios amongst these guys, okay, and that allows us to utilize trigonometry, okay? So the sine ratio, abbreviated as sine, okay, is the leg of the opposite over the hypotenuse. I'm just going to write that as O over H, okay? And where am I getting that from? Well, this one would be your opposite side, right? We're talking about angle A, and this would be your adjacent side, and this is always your hypotenuse, okay? So that's where they're coming up with these things. All right, so actually let me well, I guess that'll work. I'll put it right here, right? So the next one is the leg of the adjacent over the hypotenuse, so this one's going to be A over H. And this one down here is going to be O over H, right? The opposite of A, over A, sorry. Whoops. Okay, so actually, you know what? Let me write those down here. Okay, but those are our three ratios. And so how you come up with that is this is our opposite our angle. Okay, our hypotenuse is always directly located across from our right angle, and then the adjacent one is the side that is touching that angle we're in reference to. Okay, so I'm going to write these down here. So we're going to go sine of A is equal to O over H, cosine of A is equal to A over H, and the tangent of A is equal to O over A. And so these ratios will eventually allow us to find any sort of side or angle we may need for these right triangles. Okay, but for now we're just again focusing on the ratios. Okay, so it says using your calculator, evaluate the following. Make sure your calculator is in degree mode. Okay, I'll make sure to sort of discuss that in class and how to get there, but you need to have it in degree mode. Okay, so anyway, round your calculator values to the nearest hundredth. How do these compare to your ratios found in A? Okay. I guess I didn't want that part. No. Oh well. Anyway. So sine of 35.57. Okay. Cosine of 35.82. Tan of 35.70. Okay, and you have to make sure your calculator is in degree mode. And these are the ratios for any right triangle that has a acute angle of 35 degrees. Okay, no matter what the size is, as long as they have those two pieces of information, those ratios created by our triangle will always be the same. Okay, so as you look over here, right, there's a little mnemonic you can use, okay, in order to sort of remember these things. Okay, I just try to use SOHCAHTOA, all right, but Ms. Hellier had and Mr. Kenyon both sort of use these, so I can use these. I feel like I'll be okay, all right. So anyway, here is our ratios, right, and so here's a quick way to sort of remember it. Okay, so you can come up with any mnemonic you want. okay? But the one that I was kind of taught in school was some old hippie caught another hippie taking, well, we'll go with the tripping on acid, okay? Maybe not the most appropriate part, and so maybe if you want to change it to something different, taking, you know, the other one, taking others' apples, okay? I guess it doesn't really have that great a ring to it, but you can utilize those to sort of memorize these trig ratios, okay? So I just use SOHCAHTOA. That kind of is what always kind of stuck in my head. But if you want to use this, some old hippie caught another hippie tripping on acid, that mnemonic works good too. Okay? So anyway, for these ones down here, all they're doing is asking us to just find these values, right? So the sine of 60 is 0.866, cosine of 60, 0.5, all right? And the tangent of 60 is 1.732, okay? Sine of 45, 0.707. Cosine of 45, well, would you look at that, 0.707. We will touch on that down the road. And then tan of 45 is just going to be 1. And again, we will touch on why that is 1 down the road. Okay, but for now, that's what our calculator gives us, right? Our calculator already has those values in there. All right, so any triangle that has a 45-degree angle there, okay, the relationship created by the opposite over the hypotenuse, these sides right here, whoops, okay, will always be the same amongst all right triangles, as long as those two angles are in common, right? So this one's going to be that, right? So for all triangles that have a 45-degree angle there, okay, that relationship between the adjacent and the hypotenuse leg will always be 0.707, okay? Now, exercise 3, it says for the right triangle shown below, give the correct trigonometric ratios, okay? So the sine of r, okay? So let's start with r. So r is going to be opposite, adjacent, hypotenuse, okay? So sine is some old hippie, so in this case it would be 5 over 13. Cosine is caught another hippie, which this will be 12 over 13. And tangent, tripping on acid, okay, is going to be 5 over 12. Okay, now let's go the opposite. So now we want to find the sine of t. So what we're going to have to do is we're going to have to switch up. Now the hypotenuse stays. Now our opposite is down here, and our adjacent is up to the right. Okay, so the sine of t is going to be some old hippie. So again, it's going to be 12 over 13. Cosine is going to be 5 over 13. And then the tangent is going to be 12 over 5. Okay, so pretty much, well, as you can see, your sine and cosine both changed, and then our tangent, well, it just was sort of flipped upside down. Okay, so it says, could the measure of r equal 28 degrees? Use your calculator and your answers above to make an argument one way or the other. Okay, so when I take the sine of 28 degrees, right, the ratio that it comes up with between its opposite over hypotenuse, okay, the number we get is 0.469. Okay, so let's look at the sine of r. The sine of r, okay, what do we get for that? Well, 5 divided by 13 is 0.385. So these guys are not equal. And let's look at the cosine of 28. Well, the cosine of 28 is 0.88. So for any triangle that has a acute angle of 28, okay, or any right triangle that has an acute angle of 28, that cosine, right, that adjacent over hypotenuse ratio is always going to be 0.88. So when we look at r, we got 12 over 13. So the cosine of r is equal to 12 over 13. So 12 divided by 13 is 0.923. So therefore, not equal. All right, so therefore, because these ratios are not the same, therefore 28 cannot be the measure of angle r. Okay, so I apologize for this length. If you're watching this, you might have needed an extra reference, or you might have missed class. Hopefully this helps, okay? And we'll keep working on this one, you guys. All right, so this is probably terribly long, and I apologize, but good luck.